Bismillahirrahmanirrahim and Assalamualaikum everyone. My name is Mohamed Aiman bin Abdul Rahman. Today I would like to present my final year project which titled Simulation of Combustion in a Solar Stove. First of all, I would like to thank my supervisor which is Dr. Zainul Hilmi bin Solihin for helping me to complete this research from A to Z. Next, I would like to thank you for both panel which are Dr. Afifah binti Yahaya and Professor Maria Dr. Wan Ahmad Najmi bin Wan Mohamed. Hope you all in a good condition and stay safe during this pandemic. First of all, I would like to present the introduction for this final year project. Okay, as you all know, from a biomass cook stove have been used in many countries since decades ago. This is including whole worlds, including poor countries and rich countries. This could stop produce harmful gases emissions and lead to various types of disease for humans. This, from this condition, this lead to various studies and research of biomass cook stove design to have same objective, which is increase its efficiency and reduce its harmful gases emissions to the users. For after many years, the improved biomass cook stove already been designed and been used in many countries. The development of the biomass cook stove still being improved nowadays, and many new technologies have been implemented to this biomass cook stove, including the main cook stove that will be used in the simulation, which is solar stove. Before completing this, before start the simulation for this solar stove, I have done some research for the previous papers from several researchers that have same interest with me, which is to study about cooking stove. Okay, uh, the slide shows the some of several of the papers that have been established uh, that also same interest with the cook stove. By these papers, I have learned some of heat transfer model that been used in the cook stove. Besides that, I also have been observed some of the studies have been focused with top lift up draft cook stove, which is very similar concept with the solar stove. And some of the researchers also have been used computational fluid dynamics, which is CFD software that have been used to study this cook stove, to study the combustion in the cook stove. By using these papers, I have learned so many things that have relationship with my study. So this papers is very important as it will become the validation resources when my results from this from the software from this software. So I will refer to these papers regarding the result that have I been obtained. Okay. So from those papers, I have learned there are three popular stove that have been studied from long time ago. So first of all, we have three stone fire, which is a traditional cook stove and have many use and mostly used in poor countries such as India and Kenya. So as you can see, the design of the stove is very simple, but this stove produce many harmful emissions, and it also have used high fuel consumption and low efficiency, which is very bad for the users. Next, we have two modern stove, which is rocket stove and solar stove. Rocket stove right now have been used in many countries, and it is so efficient cook stove. And the benefit and by many researchers studied about the combustion process in the rocket stove, it have been improved and improved from time to time until now. So, so the rocket stove have been more efficient and efficient until today. So, uh, as many researchers have interest in this stove, uh, there are still many, there are still a few researchers that also interest in solar stove. From the previous researches that have been said, top lip up the cook stove is also very similar to solar stove, which uh, which are which are designed by have two separate air inlet entries. Okay, so the solar stove is almost a new improved design of biomass cook stove, and also very efficient, and it also have simple designs. From the previous research, I have been learned that there is no specific study that have been done for this cook stove combustion. Next, we move to problem statement and objective. First of all, after we proceed to the completing the final year projects, the problems have been observed from the previous research, and by doing this, so I can finalize the objective of this study. Okay, first of all, the problems that have been determined is there is no study or research that have been done that refer to solar stove geometry. So basically, the past researchers did not study did not specific study on the solar stove of the combustion in this stove, on this type of stove. Okay, so next, there is also no CFD approach to study to the solar stove. Okay, as we all know, CFD software in this time is very crucial to obtain a, a valid output data and results. Okay, so next, the optimization of a cook stove did not obtain from previous researchers. So basically, the previous research only study about the combustion in the solar stove, and only have interest in the shape only, but they did not conclude on what is the optimum input and output from their previous research. Okay, so some objectives have been highlighted for this project. Okay, there are two main objectives. First, to analyze the flame behavior of combustion in a solar stove by simulation using computational fluid dynamics software. Okay, so by using the software, we can learn and study on how the flame behavior uh, behave on this solar stove, as this stove provide two separate air inlets. Okay, so next, this study also uh, have objective where it study the relationship between manipulated fuel mass flow rate and inlet velocities towards the outlet temperature and velocities of the solar stove combustion. Okay. Next, uh, even though the simulation will be used by CFD software, uh, this project only focus on two items, which is you only use CFD software approach to study the flame behavior, which the geometry model is referred to solar stove geometry, and determine the final temperature of combustion process, which is respected to air inlet velocity. While the limitations are the fluid flow is in steady state, and in three-dimensional flow, the simulation of combustion is by CFD software approach. Wall is assumed adiabatic, no experiment conducted, verification from previous researchers, and design model in the CFD software is referred to solo stove geometry only. Okay, next we move to the methodology. Before we start to simulate, the methodology is the step and will be the guidance to have a proper method to study the solo stove, to study the combustion in the solo stove. Okay, study first of all I will clearly study the combustion process in a cook stove from previous uh, journals. Okay, next, uh, by finding the previous research journals, it will be reference it will be reference for me to get an idea how the combustion works in a stove and how the previous research uh, establish their data on their paper. Okay, by these papers, I have construct literature review and construct the mathematical model. And after these three steps, I will start the design the 3D model in CAD software, which is referred to the solo stove type. Okay, after the solo stove geometry have been modeled in the CAD software, which is CATIA, I will insert the 3D model into the CFD software that will be used, which is ANSYS. So, but in this software, I will start to meshing process, which meshing process the 3D model. After the meshing process have been done and mesh and convergence tests also have been passed for this model, I will start to insert the boundary condition and run the simulation and the ANSYS fluent. So after the result have come out from the CFD software, I will analyze the data in the CFD software and record the results in Excel software to have discussion on how the manipulated variable affect some parameters in the combustion. So, and finally, valid from the results of the CFD software, it will be validated from the previous research. Okay, so next let's move to the third step of the methodology, which is to design the 3D model of the solo stove that refer to solo stove geometry. Okay, first of all, uh, to design it, I have referred to solo stove, which is Ranger type, on the website of solostove.com. So the dimension, I have searched the dimension and the some sketches have been done on paper before I start to design it on the computer aided design software. Okay, so next step, by using CATIA, I follow the solo stove dimension when I start to design this model. Okay, as uh, as my as this so as this study only focus on the combustion in the solo stove, so I did not include the extra components of the product such as windscreen and pot stand in the design. So basically the combustion in the solo stove is start from the bottom and will flow through the outlet of the stove only. Okay, after I have been complete design it on CATIA, so I transfer it to the CFD software. Okay, in this CFD software, I will start finalize the design geometry and install it in the CFD software and save it in the CFD software program. Okay, so next, uh, schematic diagram also have been constructed where to clearly show the dimension of the solo stove geometry. Uh, next, By doing this, I can explain to the panel and my supervisor that the point on how the combustion start and where the flame flow to the end. So basically the point 1 is the hot region where the fuel will burn, while point 2 indicates the cold region. So the flame will start at the bottom and start the inlet and will flow through to the outlet. Okay, so the dotted lines show the movement of the airflow from the both air inlets. As you all can see, the as the air velocity have been injected to the stove, so it will flow to the outlet. Okay, so next, after the design model have been finalized, so in the CFD software, the mesh and convergence study will be occurred. Okay, so mesh study is very important. Okay, the meshing of the geometry will be set up and generated in the CFD software. So, in this study, the mesh elements and nodes will be varied from coarse to fine mesh. Okay, from the left you all can see, I have started the mesh from coarse to the until the right side, which is fine mesh. Okay, so by doing this, I have plotted graph which is nodes values against the output temperature. So the output of the combustion such as temperature and velocity will be observed for each different mesh. So a constant line from the graph show that the mesh precision for the simulation. Okay, as you all can see from the graph, the output temperature start to constant at 4th point where the mesh node 9393. Okay, this study helped to select the optimum mesh sizing for the combustion simulation. As we all know, uh, mesh mesh a fine mesh will produce a very long duration to complete the calculation. So by doing this, the simulation duration can be reduced when obtain the precise output values. So next, the convergence study. So the convergence study, the objective of the study is to select the best value of iteration by simulate the combustion. After we learn the best mesh for this simulation for the model, uh, the convergence study will proceed. So by choose the optimal iteration in this simulation, the duration for the calculation of the simulation to converge will be reduced. To simplify it, by doing this, I can have a short time to complete the simulation and obtain the precise values. Okay, so I will choose the iteration that start to constant until the end of the simulation. So from the graph, uh, I I have learned that the iteration start to constant at 900 points, and the mass flow rate inside the stove is constant. So by doing this, I have learned that the calculation will be complete and very near to converge at 900 points only. So next we move to the next method, which is mathematically modeling. In this method, I have used first thermodynamic law and other physical laws to model the equation of the combustion. Okay. As we all know, the first law is the net change in total energy of a system is equal to the heat added to the system minus work done by the system. The objective of the mathematical model is to find the parameters of combustion that can be calculated from the derivation. Uh, Firstly, I have been determined the energy out and energy in equation. So energy in is where the heat energy added into the combustion, where the energy output from the system is where the combination of heat energy that flow through the system and heat energy that obtained at the output. So next, the efficiency of the combustion have been used to this equation where the energy output over the energy input. So multiplication of lower heating value LHV of woods and full mass flow rate. And the next Q out is the multiplication of air mass flow rate, heat capacity, and difference between ambient temperature and temperature at the outlet stove. So as we all know, the heat transfer occurred at the from the inlet to the outlet of the stove. So the Q flow is the multiplication of overall heat transfer coefficient, stove area, and difference between outlet temperature and inlet temperature. So after I have get all the equation will be inserted back to the efficiency equation and produce the equation that you been seen in the slide. So the parameters that I can obtain from this equation is the temperature outlet, velocity average, and velocity at the outlet. So next, governing equations. There is crucial to learn that the CFD software use three-dimensional flow equation to solve the equation in the simulation. So the simulation used six equations, which are continuity equation, energy equation, momentum equation, Navier-Stokes equation, radiative heat transfer equation, and turbulence K epsilon equation. Okay, let's proceed to the results and outcome from the simulation of combustion. First of all, before I simulate the combustion by using CFD software, some boundary conditions have been set in the software. So boundary condition need to configure in the CFD software, and this condition need to set up before the simulation generated. The settings for the input parameter have been configured in the ANSYS fluids. So as you can see from the table, I have manipulated the velocity inlet and the fuel mass flow rate in the simulations. From the to to obtain the flame behavior, I have fixed the boundary set, which is fluid mass flow rate at 0.005 kg per second and temperature at 900 Kelvin, while at the same time at both air inlets at the bottom of the stove and at the side of the stove, secondary air inlet and primary air inlet, I have set the velocity to 1 meter per second, while the temperature in the room condition in room temperature, which is 300 K. Okay, first of all, let's discuss about the result from the simulation from these simulations. Okay, I have been manipulated the full mass flow rate against temperature and the output velocity, outlet velocity. So the graph shows the results from this simulation. So as you all can see from the graph, I have obtained one quadratic function, which is the temperature graph, and the linear graph, which shows the outlet velocity. So the temperature which is maximum at 921.5 Kelvin, while film mass flow rate at 0.00652 kg per second. So next, after the flame reached at its maximum temperature, it started to decrease gradually until the temperature reached to 830 Kelvin. Okay, from this relationship, so I can learn that the fuel mass flow rate increasing pattern did not produce a final high temperature at high fuel mass flow rate, but the combustion will only reach at its optimum temperature at a certain point. So this relationship become a proof that combustion in a solar stove did not need a huge fuel mass flow rate to get the best flame properties, but it needs an optimum input to get the best results. So in simple words, uh, so even though I put a very many fuels into a large fuels into the solar stove, it did not produce a very high temperature, but only it will obtain a very high temperature at a certain point only, which is the optimum point. So the increasing fuel supply into the combustion will make the flame velocities to increasing, and at the same time the fuel consumption of the combustion will be increased, which are tend to drop the flame temperature slowly. Okay, so as you all can see, when the fuel mass flow rate is is increasing, uh, let's say at 1.08, 1.009, so the temperature have been decreased a lot. So So the optimum result for the flame of the solar stove combustion can be obtained from the intersection point at the graph, which are the outlet temperatures at 897 Kelvin and outlet velocity at 2.47 meter per second, while the input flame flow rate only set at 0.0077 kg per second. So from these results, I have learned that uh, this stove did not require a large fuel and high fuel mass flow rate uh, to obtain a very high temperature. But but the users only can only can can put a low fuel or a small fuel to the stove, but still obtain a very high temperature. So in outlet velocity terms, I have learned that as the fuel mass flow rate increase, so the outlet velocity also been increased. So as you all can see that even though I put many fuels, as I put many fuel into the system, but the velocity will be increased until the end, but the temperature is decreased. So I can conclude that it is very important for for a research to find the optimum results of the combustion. So which it will benefit the users. So next, uh, a graph also have been plotted where the inlet velocity against the temperature and the outlet velocity. So from the results I have obtained two quadratic function, which is the temperature graph and outlet velocity graph. So the correlation between the relationships where the output temperature at outlet was decreased gradually as the input velocity of air increasing. So as I mentioned, the temperature line is the blue one and the outlet velocity is the uh, orange one. So the minimum temperature value was 718.05 Kelvin, while the inlet velocity at the maximum value of 2 meter per second. So the flame temperature patterns decreasing gradually when the inlet velocity increasing to the maximum. So the outlet flame velocity patterns increasing steadily when the air inlets increasing from time to time. So the intersection between the lines show the optimal flame results where the inlet velocity at 1.32 meter per second produces 7805 Kelvin and 2.2 meter per second. So from this I have learned that uh, the inlet velocity, a high value of inlet velocity did not have a good effect to the temperature of the flame, but it only reduce the reduce the temperature, but uh, the outlet velocity will be increased greatly while the inlet velocity increase. So these two output relation explain that the inlet velocity that insert into the combustion will produce a different result of output flame behavior. So a stove did not need a high velocity to get high temperature at the outlet, but inserting an optimum inlet velocity will produce an optimum outlet temperature. Okay, from these two graphs, I have concluded that inlet velocity and the fuel mass flow rate become uh, a crucial variable to the output of the combustion. So this research will have produced great results for other next generation researchers to learn the optimum to the optimum outcome from the combustion in the solar stove. So next, from the CFD software, the simulation I have simulate the temperature vector of the combustion. As you all can see, I have plot the temperature against z distance. So the z distance is where the from the what from the lower part of the stove until the outlet of the stove, which is 20 centimeter. Okay, so as you all can see, the maximum temperature at the stove is acquired at the quarter height of the stove. Okay, so the highest temperature of combustion at 0.074 meter with 975 Kelvin. So the flame temperature start to decrease when entering the secondary air inlet regions, where you all can see from the deep red color at the middle of the stove. You can see that it will turn to orange as it entered the secondary air inlet regions. Even though the temperature decreasing to the outlet, but the differences with the maximum temperature at the quarter height of the stove only 30 Kelvin. So it did not affect so much to the outlet of the temperature. So the final temperature is still excellent for any convection, as I referred to the previous research, where the 945 Kelvin at the outlet is still a very good temperature for any combustion. Okay. So from this I can say that the secondary air inlet did not affect so much to the outlet uh, temperature at the outlet stove. So next, from the CFD software, as the simulation completed in the software, a cutting plan at the center of the stove have been carried out. So as you can see, this is the center of the combustion in the solar stove. Okay, so the deep red color shows the maximum temperature of the combustion, which is at the middle. So the flame temperature reacts to the air inlet regions. So you can see uh, the air inlet is blue color, but after it move away, it move away to the stove and react to the substance that have been produced from the inlet stove, from the fuel inlet. It will turn to red color. So the flame temperature start rise to the maximum after the substance react completely towards air that been supplied from primary air inlets. So the deep red colours can be seen after the flame flowed at several distance from the air inlet areas. So from these contours, I have concluded that fluid substances need times to react completely with oxygen that supply from the air inlets. So basically, the flame will react vigorously to the air inlets. So the flame will change its behavior when it flow through the air inlet. So next we move to the cutting sections of critical regions of the combustion. So as I mentioned before, the objective of this project is concerned about the flame behavior to the whole stove of the combustion. So some regions have detected as the critical regions uh, in the stove combustion. So first of all, we have AA and CC sections where the air inlets and inlet fuels located. Next, we have BB sections where is the middle of the stove, and the DD section which is output of the stove, outlet of the stove. Next, by cutting the critical sections, the observation for the temperature controls can be met. And so by carry out these critical regions, we can study the flame behavior uh, that produce around these regions, and how it reacts with some of the inlets variable. So the detailed study on these regions will expand on how the flame behaves in the stove. First of all, let's look at the AA cutting sections. So AA section shows the inlet fuel and primary air inlet which located as the stove base. So as I mentioned at the previous, some boundary conditions have been set, which is primary air inlet and the inlet fuels, which is 900 Kelvin. But as as the design geometry, the inlet fuel have been located above a little from the primary air inlet. So this is why the combustion have occurred at the inlet fuels. So that is why the inlet at the inlet fuel regions, the yellow color is will proceed to the orange color, which is show the height temperature. So the setup temperature for primary air inlet and fuel inlets are shown in the temperature controls. So next, the BB cutting section shows the maximum flame temperature in the stove. As you all can see, the deep red colors is constant around the circle regions, which shows that there is the flame is not affected against any air or any substances. So the flame behavior is constant in these sections. So at the same time, at these regions, the flame the combustion produce a high temperature flame, which is around 970 Kelvin. So next, let's look at the CC cutting sections. In the sections, the secondary air inlets have entered into the combustions. So as you can see from the slide, uh, at the middle from the previous slide, at the BB sections it is deep red, but as it enter these regions, the deep red turn into the light orange color. So the latest orange colors around the secondary inlets show the air reduces the temperature a little bit, but as the air flow through the center of the region, the temperature start to rise again. So by these sections, we can say that the flame behavior react to the air inlets, and the temperature start uh, to drop gradually when air entered the combustion. So next we move to the DAD cutting sections, which shows the output temperature at the stove outlet. So the temperature controls it is not constant as the air injected from the secondary inlets, as I mentioned before at the CC cutting sections. So because of this, the output temperature is not constant, but uh, the height temperature still can be obtained at the center of the stove, which you all can see. The deepest orange color can be observed at the center of the circle regions. So the high temperature is still in range 930 Kelvin and 970 Kelvin, which is very excellent to the combustions. So the spots of the light orange represents the effects of secondary air injected to the combustion, and it also uh, so this simulation shows the results of how the flame behavior reacts to the air inlets in specific data. Okay, so next let's move to the velocity vectors of the combustions. So as I mentioned before, the objective of this final year project also concerned about the outlet velocity of the combustion in the solar stove. So as you can see, the image in the slide is the velocity vector of the combustion. So the flame velocity started very low from the primary air inlet and start to increase until the outlet of the stove. So the light color is have been observed from the primary air inlets, and it start increasing to the secondary air inlet regions. To have more details and more understanding about this behavior of the flame velocity behavior, let's go to the next slide. So in this cutting, in this slide, I have cut a axis plane, which is at the middle of the stove. So the light blue colors shows the input velocity, which is 1 meter per second, which can be observed at the both air inlets. So the flame velocity increasing to the outlet stove as the flame flows to the secondary air inlet regions. So the average of the flame velocity inside the stove is 1.87 meter per second and increasing to 2.49 meter per second. The outlet stove at the outlet stove based on the vector color. So as you can see, uh, the at the inlet fuel, the as the inlet fuel did not have velocity, so it will start at the blue color. But as the primary air inlet and secondary air inlets is the as have velocity at 1 meter per second, you all can see that that the greenish color at both air inlets. So uh, the combustion, uh, the flame velocity start to increase after after the middle of the stove. So as the flame entered the secondary air regions, it will start to increase to the maximum velocity. So as you can see from this uh, picture, you can see that the outlet velocity uh, will get at the outlet stove only. So I can conclude that as we put many air inlets inside a stove designs, so the outlet velocity, outlet flame velocity will start to increase, will increase at the maximum. So as you can see, the vector also illustrate the directions of the flame velocity inside the solar stove. So as you can see, the secondary air inlets will go to the outlet stove as it push from the flame velocity at the middle of the stove. So let's next move to the conclusion and recommendations. So after I've completely uh, finishing the simulation of combustion in the solar stove by using CFD software, I have some conclusion that been made for the overall project, and some recommendation also have been made up for other generation to have a future start a better result in the future. So first of all, in the overall perspective, the objective for the study have been achieved. So the combustion in the solar stove has been simulated by using CFD software, which is ANSYS Fluent. The flame behaviors inside the solar stove have been illustrated and discussed. As I have mentioned, I have cut some regions, critical regions, and also uh, a plane, and also the temperature against height of the stove. So the outlet temperature and flame velocity also been determined by manipulating the flame mass flow rate and inlet velocity. The results from the combustion simulations have been successfully tabulated in a graph and been discussed. As I mentioned before, from the graph, the uh, flame mass flow rate manipulated flame mass flow rates against the temperature and outlet velocity. The conclusion that which is critical from these results is the users have benefits, which is he can he still can use low quantities of fuels, but he can get a maximum temperature. So the most of outlet temperature from the simulation results produce a high temperature which is acceptable from previous research journals, which means I have validated the previous results with the results that I have obtained from the safety software, and it shows that the temperature is still very good and excellent, which is benefit the users. So this simulation is very crucial for the stove designer to build stove that have optimum conversions. So the conclusion is the objective have been achieved, and this study very important as these results of the study produce optimal values of inlet and outlet of the combustions. So the pre the future uh, researchers can use this study to obtain a more optimum values for of the combustions. So next is the recommendation. So for the future study, I have recommend that the simulation involve with other type of fuels such as coconut shells and tamarind pellet to study how different type of fuel affect the combustion. In this study, I have mentioned that I only use woods as the fuels and no other type of fuel used in this study. So by doing that, we can also how other fuels affect the combustion in the solar stove. It also recommended that for next study, the geometry of air inlet should be varied to study how geometry affects the combustion. In the study, the geometry of air inlets have been fixed and the inlet fuels geometry also have been fixed. So I only focus on the manipulated variables of inlet fuels and the air inlets velocity values only, air inlet values only. So in the future study, by doing this, we can obtain the very optimum solar stove geometry for the benefit of the whole world stove users. So that's all for me, Mohamed Fadhil Aiman bin Abdul Rahman. I would like to say thank you very much to both panels for hearing me out at the beginning of the presentation until the end of the presentations. So you all can contact me at inform my telephone number and email as I mentioned in the slide. So I would like to wish you all stay strong and stay safe and stay healthy uh, until the pandemic ends. So I hope we all can meet in person after this pandemic ends. That's all for me. Thank you very much. Goodbye and have a good day. Thank you.